So, good morning everybody. Maybe we can already start even though it's not 9:15 yet. But I'm a bit nervous today because I have to attend a meeting later, for which I will have to catch a train at 11:03. It's going to be late anyway, but since you don't know by how much, you have to be there. So this means I have to be at the train station at 11:03. This means I would like to stop right on time today, without a break. I hope that's going to be okay for you. I will have to wipe the board about halfway through anyway, so this gives you a chance to sneak out if you like. But I hope for your understanding that I have to run away early today. I will make up by speaking faster. No, not really. Let me return to what we did so far. We arrived at synchrotron radiation last time. The key issue was that, first of all, we wanted to have one general equation for calculating spectra. And we got that. And it was surprisingly simple formally, right? It was essentially just the Fourier integral of the component of the radiating charge's velocity perpendicular to the line of sight. But the whole complication arose because in the Fourier phase we have to enter the orbit of the emitting charge around a fixed point in space far away. All right. And then we use that in order to study, first of all, the phenomenon of synchrotron radiation, because I wanted to have one example for calculating spectra with relativistic charges. And there we saw that even though there is one specific frequency characterizing the particle's orbit, namely the Larmor frequency, we only see the emitting charge at each orbit during a very short period of time. And by essentially the same effect as the uncertainty relation, this very short interval in time during which we see the emitting charge translates into a very broad spectrum. Right? And this very narrow cone of emission allowed us to make several strong approximations, which you usually can't do with a good conscience, but nonetheless, at this particular situation, we could. First of all, since the radiation cone is so narrow, we could confine ourselves to studying the radiation in the plane of the orbit. So we could make this simplification, and then we could confine the Fourier transform that we have to do to a very narrow section of the orbit itself. This allowed us to make so many approximations that we could finally solve the problem. But these approximations are adequate if the charge is very highly relativistic. The result, let me show this here on this stupid notebook. The result looked like that. So we arrived at this modified Bessel function k of fractional order 2/3. What is that? Well, that's a certain class of solution to a certain differential equation. We'll make an approximation for that later. But if you look at the spectrum that arises once you carry out this Fourier transform that we had to carry out, you see that we get a certain prefactor here, and then we get a frequency squared times this modified Bessel function squared to the fractional order 2/3 of the same ratio of frequencies. The ratio of frequencies that occurs is omega divided by omega c. Omega c is a cutoff frequency for the spectrum. I will explain this. The cutoff frequency is 3 times gamma cubed times the Larmor frequency. 3 times gamma cubed. We are talking about charges that may have Lorentz factors on the order of 10 to the 4. Right? This is an enormous increase in the frequency range. All right, I recall here that the Larmor frequency was EB divided by gamma MEC. So you see, even though you have this 1 over gamma here in the Larmor frequency, we have a factor of gamma square winning in the cutoff frequency. This is quite enormous. This is one very important characteristic of synchrotron radiation. All right, now, the modified Bessel function here of fractional order 2/3 allows for large arguments this particular approximation here. It's a very simple approximation, which we are going to use later on again. It's square root of pi divided by 2x e to the power of minus x. The order does not enter. Right? This approximation here is independent of the order of 2/3. This is valid for all of these modified Bessel functions of type K. This will reappear later. We are going to use this. Yes?
Both of them or just the lower one?
The lower one. Yes. So this asymptotic approximation for large arguments, this is valid for all orders of the Bessel function K. This is not. So the small scale behavior is not. Now let me, without further ado, just show you this spectrum. This is the Bessel function in blue. The orange dashed line is the low argument approximation. The green dashed line is the high argument approximation. You see how well this essentially exponential cutoff represents the Bessel function. This particular Bessel function. All right, now if you look at the complete spectrum, we have an omega square times the k. So this rises like a power law, and the power law is, as you can see here, 2/3. That's given by the order of the Bessel function, and then you have this exponential cutoff around the cutoff frequency of gamma cubed times the Larmor frequency. All right, now what is this exactly? This is the spectrum emitted by a single electron. But usually you have two or more. So what you will see is not exactly that. But what you will see is the superposition of spectra of all the electrons included in your electron population, weighted by the abundance of these electrons as a function of Lorentz factor gamma. Right, so you fix a distribution of the electrons parameterized by gamma or by electron energy, which is equivalent, and then you get a linear superposition of all these spectra. Now we have to do here, and this was one of the primary assumptions that we made, we have to do with very energetic electrons. So the question is, how do you get them? And the answer is, in many cases, we don't know. But typically, in stochastic acceleration processes, such as, you may have heard about this, you may not, but this is not so important for us, such as Fermi type 2 acceleration, right, which is a stochastic electron acceleration process, you get a power law spectrum. And you get the power law just because getting more energy is probability for a second or third or fourth collision that the electron experiences. So this gives rise to a power law. So usually you have a power law distribution for very highly energetic electrons. And on the next problem sheet number 2, you will find the calculation that I'm summarizing right now. So if you superpose this spectrum here with the power law distribution of electrons, you get another spectrum, which is a power law. A power law with a specific exponent that we are going to ask you to work out. Okay? So power law spectra are typical for synchrotron emission, not because the individual synchrotron spectrum is a power law. That's not the case, right? It is a power law with an exponential cutoff, but because the underlying electron population has a power law in energy or Lorentz factor. All right, another thing I haven't talked about at all is the following. I said, because of the focusing of the radiation into the forward direction of the electron, we can confine ourselves to the orbital plane of the electron. All right. And there we saw that the only component of the electron's velocity that is relevant for us is the component in the motion of the in the plane of the electron's motion. This means that the radiation spectrum, the differential Larmor power, only has a component along the projection of the orbital plane on our sky, right? This is a line. So this means that typically synchrotron radiation is very highly polarized, linearly polarized, perpendicular to the orientation of the magnetic field. This is very intuitive, I think, right? The electron goes round in a circle, and you see almost linearly polarized emission in the synchrotron radiation. So these are the two important criteria to identify synchrotron radiation. You typically see a power law and you see highly polarized radiation. And you have a power law over many orders of magnitude. This is because if the charges are very highly relativistic, the spectrum broadens enormously. All right, very important. Do you have any questions so far? Then I have questions for you. They are going to be summarized on problem sheet number 2. All right. Then let me say a few words about how we are going to continue now. And for that, I'm going to show you the table of contents of this book that underlies our lecture. We are in chapter 2, you may have noticed that. We talked about Thomson scattering, we talked about how to calculate spectra, we talked about synchrotron radiation now. Today, maybe for parts of Wednesday also, I will talk about Bremsstrahlung. That's the English word. The German word is Bremsstrahlung. Sometimes you hear the English term free radiation, because the electrons go from a free state to a free state. I would like to cover part of this chapter on radiation damping, because we need it, and on Compton scattering. Let's see how far we get. We have 3 weeks for radiation processes, and I would like to talk about quantum processes and shapes of spectral lines as well. So I will leave out parts of what you find covered here. Also, if you think of Bremsstrahlung, right, the situation you have in mind is that, for example, you have a proton, you send an electron past the proton, it's going to be deflected. What's the orbit? On what orbit is the electron going to fly past that proton? On a hyperbola, exactly. Why? Why is it going to be a hyperbola? Think of Kepler's problem. Theory 1. What classes of solutions could we get? Closed solutions on an ellipse, closed solutions on a degenerate ellipse, called a circle, open solutions on what you get from an ellipse when you replace the cosine that appears in the denominator by a hyperbolic cosine. It's going to be a hyperbolic orbit. So what would we have to do if we were to, you see the subjunctive, right? If we were to calculate Bremsstrahlung exactly, we would have to insert a hyperbolic orbit into the Fourier phase of our spectral calculation. This is possible. It leads to so-called Hankel functions. They are complex linear combinations of Bessel functions and so on. And it's a very complicated calculation. You find that in the book. I will do something different today. Right? I will go through a very much simplified calculation, which leads to a result which contains all the right dependencies, but a wrong amplitude. This is due to the simplifications, but you will see all the necessary ingredients without going through the really complicated details of doing the exact calculation. Okay, so this will be part 1 of today, and then we will see about radiation damping and stuff. But let's start with that. Bremsstrahlung. So you see, if you really want to look this up, and I hope you feel the urge, right, as soon as this lecture ends, have a look at section 2.4. It looks awful, I understand. Nonetheless, maybe you like horror movies. Okay. Bremsstrahlung. So again, what actually is going to happen is that the electron is flying past the proton on a hyperbolic orbit. Okay, good. For presenting this in the lecture, the actual calculation is too complicated. I'm going to use Born's approximation instead. Remember Born's approximation? See, we need to carry out, or we need to calculate the acceleration of the charge. Right? Because the Fourier transform of the acceleration of the charge goes quadratically into the non-relativistic Larmor spectrum. I should have said this, right? I want to apply this situation now to a non-relativistic electron population. That means to an electron population where the energy is very much smaller than the rest energy of the electron, or 511 kiloelectron volts. So for example, I'm thinking of a thermal electron population whose temperature then has to be much less than approximately 500 kV, or kBT has to be much less than approximately 500 kV. This is often applied to, for example, the hot plasma in a galaxy cluster, right? And I showed you for motivation at the beginning, and their typical temperatures are of order 10 kV. Right, so typically we are well in the regime of non-relativistic radiation. All right. So if I take the Larmor power for that, that's going to be 2e squared divided by 3c cubed times the acceleration, Fourier transformed, absolute squared. Now, Born's approximation consists in evaluating the acceleration of the particle, not along the actual path of the particle, not along the actual trajectory, but along the unperturbed trajectory. Right, so we let the electron fly past the proton along a straight line, and we are going to evaluate the acceleration along that straight line. So we are going to do that. This is the trajectory along which we will evaluate the acceleration. Now, what is that? I'm going to characterize this straight line here now by an impact parameter b. That's the smallest separation that the two are going to have. And then I can describe the orbit by saying, okay, the particle moves with the velocity v such that it covers the distance vt if I call the point of the time of closest approach t equals 0. Then I know what the separation is between the two. So the separation is just given by v squared t squared plus b squared square root. Then I know what the potential is like. That's the electrostatic potential. That's going to be given by E over R. Then I know what the force is. And now the force is going to act perpendicular to the the unperturbed orbit. And then I have to take the B derivative of phi. So that's the perpendicular force here. And this is going to be, minus E times plus E times dB phi, right? So in order to get the force, I have to multiply with the charge of the electron. That would be minus E. But I would have to apply the negative gradient, so this gives me the positive sign. Okay, so the force is going to be, and I take the absolute value of it, E squared times B divided by V squared T squared plus P squared to the third power. Okay, and this is almost already the acceleration, right? So what we have to calculate, I'm going to write the absolute value here, A tilde of omega, this is just going to be E squared divided by electron mass. These are the constants. And then I will have to integrate over B divided by V squared T squared plus B squared to the third power, e to the minus I omega t, and I will have to integrate over dt between plus and minus infinity. That's the integral I have to solve. Before we do that, let us transform this a little bit, because then Mathematica will more easily understand what you want. I'm going to factor out the b square here, so that I can pull the b cubed into the denominator. This will cancel this b, and I will have a b square left. Then within the square root, I will have v times t divided by b squared. So I will introduce an abbreviation for the quantity that's going to remain. I will call this tau. Then, of course, I will have to integrate over dt, so I'm going to translate this into an integral over d tau by saying dt is b tau over v times d tau. Sorry. B over v times d tau. All right. Then, of course, I will have to do this transformation here as well. And then I will get a quantity which I will call z, which is going to be b omega divided by v, so that when I insert this transformation and I transform this Fourier phase to tau, I will just get z times tau in the exponent. All right, so with these substitutions, let me just continue underneath here. With these substitutions, I can write a tilde of omega. Now let me collect all the factors that are not integrated over. That's e squared over me. Then I will have a factor of 1 over b squared from pulling the b squared out here. Then I will have a factor of b over v from the transformation of the integration variable. And I will have an integral of e to the minus I z tau divided by square root of 1 plus tau squared to the power of 3, integrated over d tau from minus infinity to plus infinity. Aha. Well, now, either you look this up or you ask Mathematica for it. You can simplify this a little bit. You have cosine z tau plus I times sine z tau here. The sign is odd, it's antisymmetric. The denominator is symmetric, so the integrand is antisymmetric, so the sine part disappears. You could therefore write as well, write cosine z tau divided by 1 plus tau square root to the third power. Gives you the same result. The result of this is 2 times absolute value of z modified Bessel function of type k of order 1 of the absolute value of z. Now we do not have a problem with the absolute value of z, right? Because b is positive, omega is positive, v is positive. Okay. So what do we get? We get that this is 2 times e squared divided by me b v. And then b omega divided by v, that's this factor here, times k1 of b omega divided by v. Okay. So I can cancel a little more. The b is going to go away. I get 2e squared times omega divided by me v squared k1 b omega times v. Okay, this is our Fourier transform under the assumption of Born's approximation. Now, Born's approximation is going to be valid if the impact parameter is not too small. If the impact parameter is very small, the deflection of the electron is going to be large. This will give us trouble in a few minutes. So we have to fix that trouble before we move on. But the trouble is only caused by ourselves, right? By using Born's approximation. What else do you see here? First of all, if you get a result like this, check the dimension. See whether you believe that. What dimension do we expect for a Fourier transformed acceleration? You integrate an acceleration over time, right? Because the Fourier factor has no unit. So the acceleration has length divided by time squared, so if you integrate this over time, the Fourier transformed acceleration should have the dimension of a velocity, length over time. Does it? Let's see. MEV squared is an energy. E squared is an energy times length, right? Because in our units, the Coulomb energy, for example, is just minus E squared divided by R. So E squared on its own is an energy times length. So we have an energy times length divided by an energy, that's a length, times a frequency, that's length over time, that's velocity. At least the dimensions are correct, right? Okay. So now we, let me call this A0 here because A0 tilde, because it's just a lot of numbers. Now let us insert this into the Larmor power, or rather directly into what we got for the non-relativistic Larmor spectrum by using the non-relativistic version of the Larmor power. This is going to be E squared divided by 3 pi c cubed A0 tilde square K1 square B omega times V. Okay. This is now what? This is the Bremsstrahlung spectrum emitted by a single electron under Born's approximation, passing a charge E, appropriate for a proton. It might pass a charge Z times E, appropriate for a helium nucleus with Z equals 2, for example. Right? So let me write down here Well, let me introduce an additional factor Z, which is the charge number of the nucleus that is deflecting the electron. Okay? We could have started with the Z right away at the potential phi equals ZE divided by R and carried through. Right? Okay, now this is the emission of a single electron meeting a single proton. Okay, good. Now, an electron moving with velocity v embedded into a plasma has a certain chance to meet more than a single proton. How many? Okay, let's see. Electron moving with velocity v within time dt is going to cover the length v times dt. Since it interacts with another charge, we attach the Thomson cross-section to it. No, sorry. That's what, forget that, please. Electron is moving. All right. Now it's flying through a plasma which has a certain density. Let's call it Ni of ions that it's flying past. Now, I need to know how many ions will be contained in a narrow ring with radius b and width db. So this is dB, okay? So the volume that the electron carries around with this ring of radius b and width dB is v times dt times 2 pi b dB. This is the volume that the electron is covering by flying through. Now if I multiply this with the number density of ions, I will get the number of scattering events that the electron will experience within time dt. And each time, I'm assuming, it's going to emit this energy here. Right? So if I'm asking not for the energy per frequency of a single electron and proton scattering event, but of the energy per frequency per unit time that the electron is going to emit by flying by all the ions that it finds, then I have to multiply this result here by this beautiful expression. So from these two considerations, I can conclude that now the energy emitted, d2e, per unit time and unit frequency, this is going to be 2 pi, cancels with 3 pi here, gives a factor of 2 over 3. Then I have z, e squared, ni, v. The v is going to occur here as well, so careful. In any case, we have ze squared divided by c cubed from here, multiplied by ni. Now we have b dB times v. Then we have a0 tilde squared. And we have the inevitable Bessel function here. All right, this is not quite complete, right? These are the numbers, the number of ions that the electron flies past at impact parameter b with the width dB of impact parameter. Let me see, did I collect everything? should be okay, right? So, k squared. All right. So now we should integrate this over all impact parameters from 0 to infinity, right? Because the scattering ions could be anywhere. Of course, they cannot be at infinity, right? Because you have no plasma that is infinitely extended. However, infinity means far away from the impact parameter, right? At very many impact parameters. Because, as you saw, the Bessel function for large arguments goes down exponentially as well. Right? So the large impact parameters are not our problem. Of course, the small impact parameters are our problem, right? Because we have made an approximation that excludes small impact parameters. And the small impact parameters, you would expect the hyperbolic orbit, we have assumed a straight line. We have assumed Born's approximation. And therefore, you can in fact integrate this out. This is no problem. But if you then drive the lower integral bound to 0, it's going to explode. And for good reasons, right? There's no physical reason why it explodes, but the reason are again ourselves. Right? We have made an approximation that we are now about to violate. So what could we do? We could either integrate from a small enough but finite impact parameter to infinity, or we could say, all right, I'm going to insert the approximation for large impact parameters that we had before. Both are in the framework of our approximations sensible things to do. So let me write down the square of the approximation for all these modified Bessel functions that we had before. Right? Now if I insert this, I can very easily integrate this out. You cannot expect to get the right amplitude in this way, but you can expect to get the right scalings of all the involved quantities. Okay, so I'm going to introduce also as an integration variable the variable z equals b omega divided by v. So I can write here the b dB. This is of course a z dz times v squared over omega squared from the transformation of dB to dz. Aha. But now I have to write this out, right? Now I have to write the A0 tilde square out, because in the A0 tilde there's a v square appearing that we now have to take explicitly into account. All right, so what are we getting now? Here's a factor of 1 over 2. Here's a factor of pi. Here's a factor of 2/3. This gives you pi, or gives us pi over 3. But then the A0 contains a 2. Since we have to square it, gives us 4 pi over 3. Okay. Then we have a set e square. We have an e square here, but we need to square this. So this gives us set e to the power of 6. We have an Ni, the ion number density. We have me squared c cubed What else? We have an omega over v squared. So we have an omega squared divided by v to the power of 4. We cancel the omega squared. We have 1 over v to the power of 4. We multiply this by v to the power of 3. We get 1 over v. Have we got everything? I believe it. So what remains is now the integral from 0 to infinity of z dz. We have taken care of this factor. We have taken care of the pi over 2 as well, but here is a factor of 1 over z. So what remains is just a dz over e to the minus 2z. But this is easy. That just gives you a factor of a half. And we already took into account that we have to square the modified Bessel function. So this just gives you a half. And what remains is 2 pi over 3. Z e to the power of 6 ni divided by me squared c cubed v. That's a relatively nice formula. But we are not at the end yet. This is now the energy emitted per unit time and unit frequency by a single electron. We might have more of them. So we need to multiply with the electron number density as well. If Z is 1, then of course the two are equal. Ne equals Ni. And you see a very important scaling here already. The Bremsstrahlung emission goes like number density of the charges squared. It goes like 1 over v. Interesting. It goes like 1 over the electron's velocity. The faster the electron is, the less it emits. Because the relative acceleration doesn't matter so much anymore. Right? If you wish, the time of encounter between the electron and the proton or the ion is going to be the shorter, the faster the electron is. This has interesting consequences. We see about that. And the rest is just energy scaling here. All right. So now let me do the following thing. Let me cover the rest of this board here with a transition from the energy emitted by a single electron per unit time, per unit frequency, to the energy current density emitted by the electrons. So this would be sorry, it's not a current density, the emissivity, is it usually called? Emissivity. That's energy emitted per unit time, per unit frequency, per unit volume. Okay? Erg per second per hertz. Hertz is 1 over second, right? Don't even think of canceling them. What else? Centimeters cubed, right? Because then you know how much each cubic centimeter is going to emit. Okay, now I could just reproduce that. Depends on things. 2 pi over 3 Z e to the power of 6 Ni. Okay, fine, we had this before. Now I have to multiply this with Ne, right? The number density of the electrons as well, because what we calculated so far, what is down in the bottom line, is the emission of a single electron. I multiply with the number of electrons I have per cubic centimeter, and what I get is the emissivity in units of energy per second per hertz per cubic centimeter. Okay, what do we have? Me squared c cubed 1 over v. What do I do with the 1 over v now? I average this over a thermal electron population. Okay, so I'm assuming I have a thermal electron population. Then the electrons have what kind of distribution? Velocity distribution. Thermal equilibrium. Velocity. Maxwell-Boltzmann, exactly. All right, so I'm assuming they're going to have a Maxwell-Boltzmann distribution, then I have to average the 1 over v over the Maxwell-Boltzmann distribution here. Okay. Where's the frequency? The frequency is gone. The spectrum is completely flat. Do you believe this? Do you believe this? The spectrum is completely flat. So it goes to infinite frequency. Hell, this can't be, right? What did we do wrong? Again, okay, let's see about that. Good. So now what remains is that we have to calculate the average, the thermal average of the 1 over V. Okay, good. How would we do that? We would do something like this. Right? We would take the Maxwell-Boltzmann velocity distribution P of V, and we would carry out this integral here. Aha. Well, let's do that then. P of V. The essential element of the Maxwell-Boltzmann distribution is the exponential decay. Right? It's the Boltzmann part of the Maxwell. So this must go like exponential to the power of minus V squared. Divided by what? Well, you need to take the kinetic energy of the electron, MeV squared divided by 2, and scale it with the thermal energy 2 kb over 2 kb times T. Sorry, kb times T. Okay, fine. This is a Gaussian. If you want to normalize that Gaussian, you need to identify the sigma square and put the sigma square into normalization factor. What happens is you get a normalization factor of 2 pi cubed, that's by the three-dimensionality of space. And then we get a sigma yes, sigma square to the power of 3. And sigma square is going to be kBt divided by me, and that's also going to be times the power of 3. All right. This is Maxwell-Boltzmann correctly normalized. This is not exactly what we need because we have an isotropic distribution here, right? We integrate over all directions of the velocity just because there is no preferred direction in the Maxwell-Boltzmann distribution. So I'm going to replace this here by V squared dV. Then of course I can carry out the solid angle integral, which will just give me a factor of 4 pi. I'm going to pull this into the normalization of the P of V. So I'm getting this here for the Maxwell-Boltzmann distribution now of the absolute value of the velocity. Right? Not of the three-dimensional velocity, but of the absolute value of it. Okay. So our averaged 1 over V is now going to be what? It's 4 pi divided by 2 pi to the power of 3 under the square root. I'm deliberately not cancelling anything right now. I'm just going to copy all of that. kBt divided by me cubed square root. Very well. Then I have to integrate over V squared dV divided by V, so V dV. And I'm calling this dV squared divided by 2. Okay, so the differential now applies to V squared. And then I have the exponential of minus a times V squared. If I call a equals me divided by 2 kBt. Well, this is very easy, right? It's just an exponential integrated. This gives me a 1 over minus a. I need to evaluate this at 0 to infinity, and I'm done. Am I? Can I really integrate from velocity equals 0? I shouldn't do that. First of all, you see that result here is scaling with 1 over v. So this would mean if we drove the velocity to 0, we would get infinite acceleration. But we have assumed Bond's approximation, which means that the acceleration, or the difference between the actual acceleration and the acceleration evaluated along the straight line is negligibly small. So we need to integrate from some finite minimal velocity to infinity. And we can safely go to infinity because the faster the electron is, the less it's going to be deflected. That is fine. The upper integral bound is fine. The lower is not. So how do we set this? We need to require that the kinetic energy of the electron is at least enough to emit a photon of frequency h bar omega. There are quantum effects entering necessarily, right? Because the electron flying past the source, the ion, needs to be at least as energetic so that it can emit a photon of energy h bar omega. Okay. See how nicely this works out. So I can continue writing underneath and say, okay, first of all, the thermally averaged 1 over v is now the following thing. It's 4 pi divided by 2 pi cubed. Now I did introduce a quantity A which reappears in the normalization factor, right? Because the normalization factor is just one over 2a cubed. Okay, that was not so important. Then from the transformation from v dv to dv squared over 2, I gain a factor of 2 pi, which cancels with a 4 here. Then what remains is just an integral over an exponential of minus a times the argument that I'm integrating over. So this gives me a 1 over a evaluated at 1 over a times the exponential minus a times minimum velocity square. Okay, that's fine. Now, let's see. I'm now pulling this a as a square under the square root. This cancels most of that. The 2's cancel each other. The pi's cancel most of them. Anyway, what I get now is square root of a. That's what remains of these factors here. I get square root of pi, and I get a factor of 2. Exponential of minus a v min squared. Okay, now let me reinstall all the constants. This is 2 over root pi. Now the square root of me divided by 2 kbt okay. This this will do that. Then we have the exponential of minus v mean square. V mean square is 2h bar omega divided by me. So what remains is just an h bar omega divided by kBt once I insert the constants. Are the units correct? Well, first of all, this is a mass, this is an energy. So I'm dividing a mass by an energy. This is 1 over velocity squared. I take the square root, it's 1 over velocity. Okay, good, that's what we wanted to have. The mean velocity is characterized by the temperature. Very well, what else would we have expected? But then we get an exponential cutoff with the temperature. Right? We get a spectrum that is essentially frequency independent until it reaches an exponential cutoff, because the electrons belonging to a thermal distribution at temperature T are not energetic enough to emit more energetic photons. So now let us collect the results in a little box here. So what we now have is the Bremsstrahlung emissivity. Now this is for a thermal plasma at temperature T. We could have done something else, right? We could have used a different velocity distribution of the electrons to integrate over. Then we could, for example, get any kind of non-thermal Bremsstrahlung radiation. But for thermal Bremsstrahlung radiation, we get a very characteristic result that's very often used in astrophysics. Where are we? I'm going to copy from above. Let me call this JFF, right? Free. This is 2 pi over 3 times root 2 over pi. These constants are going to be wrong, right? Because we cannot expect to get the right normalization of the spectrum due to our approximations. The rest of the scalings is completely correct. This is Z times e to the power of 6 NI divided by me squared c cubed, and now the average of 1 over v, except for this prefactor root 2 over pi, which I already have. So this is root me divided by kBt, exponential of minus h bar omega divided by kBt. I told you there are quantum effects that you have to take into account. If you do this correctly, you get a correction factor, which is called the Gaunt factor. Gaunt factor. In all applications that I've seen so far, it is a good approximation to say GFF is 1. Okay? This is what I wanted to show you in the first part of today. This is Bremsstrahlung emissivity. Right? So we talked about 2 different subjects. Right? We finished synchrotron emission. The important part was the shape of the spectrum. I said it's going to be modified by the electron energy distribution, and usually you get power laws for synchrotron emission. And you're going to have linearly polarized radiation. That was synchrotron. Then we said, okay, if we want to calculate the Bremsstrahlung spectrum exactly, we will have to insert a hyperbolic orbit, the hyperbolic orbit of an electron flying past an ion, which you can do. Lengthy calculation. We abbreviated this by saying, all right, we are going to evaluate the electron's acceleration in Born's approximation. That means we are going to evaluate the acceleration along a straight line. We could do the Fourier transform right away. Leads us to a Bessel function. We make a mistake here. Right? We cannot treat small, very small impact parameters. Nonetheless, we need to integrate over impact parameters. In order to do this, we make the asymptotic approximation of the modified Bessel function for large arguments, then the integral convergence, we get this result here. Then, in addition, integrating over velocities, we have to take into account that very slow electrons do not contribute. We need to have a minimum energy in order to emit a photon of frequency omega, and this gives then rise to this very particular form of the thermal Bremsstrahlung spectrum. It is frequency independent for a large range until you reach the thermal cutoff frequency, right? The frequency allowed by electrons with a typical temperature T. And this means, and now let me show you a picture. See, calculation, calculation ongoing. Now we arrive at this. And these are typical Bremsstrahlung spectra observed from thermal plasmas at different temperatures. Observed is not quite true. Modeled by software according to observations. Okay? And you see 4 curves. Let's look at the let's look at the red and the blue curve at first. There you see y equals 0. Why there's a y, I'm going to explain. KT equals 1 kilo electron volt, kT equals 5 kilo electron volt. And you see, okay, if you make the plasma hotter, the cutoff frequency shifts to larger values, obviously. It's going to turn almost flat, right? What you see is the onset of the exponential cutoff. What you see here is the exponential cutoff of the spectrum. These are typical spectra that you observe, for example, from the plasma in galaxy clusters. Except that there you see a lot of lines in addition. And this is why I first calculated spectra with y equals 0. Y is the so-called metallicity. And I guess you know that in astronomy everything is called a metal that is heavier than helium. Yes. No, sorry. Y is the... Yes. Okay. So this is hydrogen emission, right? Y equals 0. Now I increase the metallicity to 0.25. This doesn't tell you about the mixture of elements. Right? It's 0.25, the solar mixture of elements. All right. If you have a hot plasma, the lines don't matter that much. And what dominates is the Bremsstrahlung continuum spectrum. If you have a cool plasma, you see a lot of lines. And this is typically what you observe. So typically you observe spectra like this. You see an exponential cutoff. This is the decisive criterion for thermal radiation, the exponential cutoff, right? You see the Boltzmann factor everywhere, also in the sky. So by the location of this cutoff in the spectrum, you get a first estimate of the temperature. But usually the spectral resolution at these energies is relatively low, so you can't determine the temperature very well. What helps is the intensities of the lines that you see on top. And how they depend on temperature, we are going to see later. All right. Do you have questions about this derivation of the Bremsstrahlung spectrum? Again, right, you can do it correctly. If I did this in the lecture, you would fall asleep. And you would fall solidly asleep for about 2 hours. That's a waste of time. What is important to see is the steps that we have to carry out. Right? And we have to carry out always the same steps, right? We have to describe the electron's orbit or the electron's acceleration. We can do both, I showed you. Sorry, we can do either one. We can do both as well, but that's also a waste of time. Then you can carry out the Fourier transform and you immediately know what the spectrum is like. But this has been the spectrum of a single electron scattering off a single ion. So then we had to extend the calculation, first of all, by introducing all the ions, then integrating over all impact parameters with the problems we encountered, then by integrating or averaging over the electron velocities. And in averaging over the electron velocities, we had to acknowledge that we should take quantum effects into account, but don't want to. We put the lack of knowledge into the Gaun factor. We see, it's tabulated typically, we see from these tables that the Gaun factor is typically 1. We get the right scalings out, right? It scales with Z. So the charge number of the ions. What do you do if there is a mixture? Then of course you have to average over that as well. Okay, it scales with the number density of the electrons and the ions squared. So typically it scales with the gas density squared. It scales like 1 over the square root of the temperature. And it has an exponential cutoff. These are the, one second. These are the main results that we can get. The prefactor here is going to be wrong, right? So don't believe that. But the rest comes out right. Yes.
Why is Bremsstrahlung called Bremsstrahlung if the electron is accelerated?
I don't know. Yes, I do know. Wait a moment. I do know. This comes from the first applications of Bremsstrahlung when you send a ray of electrons on a cathode to produce X-rays. And there the electrons crash into the target cathode and are in fact stopped. You're right, I mean, they are not bremsed, right? Because they keep their energy, of course, in this encounter. But in the direction of flight, they are becoming more slow. Slower. Good. Yes. Speak louder, please.
So this is the x-axis is right?
Yes. That's the exact calculation. In fact, these curves are produced in 2 ways. Those with the lines I calculated with XPEC software. This is software that has been made for the analysis of X-ray satellites.
The question is, so we saw that this approximation is not very good at right?
Then I misunderstood you. What enters here is the calculation without approximation.
What happens with the 0 after 0?
The curves become very flat, and then they turn gently over. The spectrum goes approximately like that. Yes?
Just a question to the minimum velocity. I'm not really sure what the frequency range that we're committed to has.
All right. So the question was about the minimum velocity and the frequency range that we have to consider. So the frequency is set by the thermal energy of the electrons. So if you wanted to know what is the central frequency, for example, that would be set by setting h bar omega equal to 3/2 kBt. This gives you the central frequency. And now you know you have essentially a Gaussian distribution of velocities around that. So if you go to plus or minus 3 sigma or so, you know that you have covered approximately 99.95 sigma, approximately 99.99 times the energy emitted. So the scale is set by the temperature.
Another question on top of that. Do we have any fear that if we're getting very close to 0 to the point that it makes our approximation?
Well, this approximation is just for illustration. And if you want to do it right, then you have to take the Gaun factor into account. and you have to take the hyperbolic orbit into account. This is the derivation that I've shown you is an approximate derivation to illustrate the principle. The exact result. See them? Hankel functions. Very beautiful. Of complex order. Isn't that nice? It's horrible. Yes. Oh dear. So 2, 126 is the exact result. And you see, even including the normalization, we are not so bad. But nonetheless, the normalization is not correct. Also, in this calculation here, in this formula, you see V infinity, where I have used V in the calculation here. This is because along the actual orbit, the velocity is going to change. Along our orbit, the velocity is not going to change. And so what I call V here is the V infinity that appears here. Okay? So for example, you look at a galaxy cluster, or somebody gives you a galaxy cluster for Christmas or whatever, and you want to know how hot is this galaxy cluster. You take an X-ray spectrum. We are in the soft X-ray regime here. Why does a galaxy cluster have that temperature? I mean, this temperature must correspond to the depth of the gravitational potential, right, due to the virial theorem. And since the galaxy cluster is what it is, right, it has a certain depth of the potential well, the plasma must have a temperature in the keV range. There's soft X-rays. And if you go to the doctor and you want to have an X-ray made, energies go up to 30 keV or so. Right, so for medical purposes, galaxy clusters are not really useful. Nonetheless, right, you take a soft X-ray spectrum, and the typical X-ray spectrum of X-ray satellites is precisely adapted to that. Right? Typically, the photon energies that they are able to receive go from 0.2 to approximately 15 or 20 keV. And they cover this pretty much that range that is pictured here. Then you see, then you can derive the spectrum. Then you see, first of all, the lines excited. We're going to speak about lines in next week. And you see the exponential or thermal cutoff in the spectrum. And the thermal cutoff tells you, okay, the assumption of having a thermal plasma is not bad. The location of the cutoff and the excitation strength of the individual lines, they tell you about the temperature. And of course, if you want to have a precise calculation, then you use software that other people made. Yeah. Yeah. The question was, why did we introduce the Gaun factor here? The result is, or the reason is that by here we go. By setting this lower velocity limit here, we only approximately take quantum effects into account. Right? We say there is a quantum effect because the accelerated electron must at least have the energy of emitting one photon. But there is more to it, right? You need to do a quantum mechanical calculation if you want to get this right. And we put all uncertainty that we acquire by making this assumption here into the Gaun factor. And then fortunately it turns out to be 1 for most of the applications.
Is the fact that the Gaun factor mostly equals 1 experimentally measured, or can you derive it theoretically?
You can derive, so the question was, where do you get the Gaun factor from? You derive it theoretically and you can measure it. And you find agreement. Good. Anything else about synchrotron and Bremsstrahlung? You see, these were my 2 examples for illustrating how you calculate a spectrum. The overall theory is much more complicated if you want to apply it correctly, but these are the 2 main applications, right? We had one application where we could make the extreme approximation of having a signal only very short each orbit, and that allowed us to make a lot of approximations. Also, we made approximations here, right, in calculating the Bremsstrahlung spectrum. The complete calculations are elsewhere. Yes. Why do you?
Taking into account like the electrons interacting with the atoms, but what about the electrons interacting with other electrons?
You should also have Bremsstrahlung by the scattering of electrons about electrons. This is a much more complicated problem. Because, of course, then you can't make Born's approximation at all. Right? And the emissivity of the electrons, scattering of electrons, is very much lower. And therefore, it's usually being ignored. The Bremsstrahlung contribution of scattering of electrons by electrons is usually just neglected. All right. Are we through with that? If that's the case, then I'm going to wipe the board, and we are going to continue right after I'm done with that. Sorry for that, you know why. But it's your break. All right. Can we move on? Now I would like to consider the following problem. No. All right. Suppose I have an electron that is running into a thermal distribution of radiation. Is there such a thing? Well, of course, right? If I have a thermal plasma, the plasma will be a mixture of the particles and the photons. I have the cosmic microwave background, for example, which is an exactly or almost precisely isotropic sea of radiation. Okay, so suppose I have this collection of photons here, thermally distributed. Could be another distribution, but let's start with thermal. And then I'm sending an electron into that. What's happening? Well, first of all, I have the electric and the magnetic field of that thermal isotropic sea of radiation, which is going to accelerate the electron. It's not going to be very pleasant for the electron. It just experiences lots of kicks. It's going to be accelerated. It's going to radiate. So it's losing energy into the radiation field. It's going to heat up the radiation field by losing its own energy. I want to know how much energy does this electron pass into the radiation field, which I could use, for example, to address the question, how far can an electron propagate before it's lost all its energy? This is one thing. And then we need to think of the reverse process as well, right? Because we haven't studied this so far yet, but each photon that kicks an electron also passes momentum to the electron. So I have also the reverse process, right? I have a heating process of the photons by the electrons, and I have a heating process of the electrons by the photons. Who is going to win, by the way? Let's see. So this means we are now we are about halfway through 2.5. 2.5 starts with a section that I do not want. You could have said a word. Okay. If you want to look it up in the book, go into section 2.5. 2.5 starts with a consideration that I don't want to repeat here because it's of less importance for us, but nonetheless, have a look. Okay. Morning. So first of all, I have to consider two rest frames, right? I have a rest frame in which I'm assuming that the photons or the radiation, you see, I'm gradually moving from a wave description of light to a photon description of light. This is intentional. But okay, you have one frame of reference for the photon distribution in which I can assume that this photon distribution is isotropic. Of course, if you move with respect to it, it's your own fault, right? Then the photon distribution will not be isotropic anymore by Lorentz boost. Okay, so we are assuming that we have a rest frame of the photons. And in this rest frame, I'm going to assume that the average of each individual component of the electric field in that rest frame is going to be 0. Otherwise, if that was not the case, I would introduce preferred directions, which of course would contradict the assumption of isotropy. Good. This then must also apply to all components of the magnetic field. In addition, I'm going to assume that electric and magnetic field components are not correlated. What I cannot discuss away is that the averaged squared electric field components, they must add up to the complete energy density. So this is going to be 4 pi over c times the energy density in the electromagnetic field. And the same must hold for the squared components of the magnetic field, because we have electromagnetic radiation in vacuum, for which E and B have the same magnitude. So these are the assumptions we can make in the photon rest frame. But now we shoot this electron into this distribution of photons. If we agree on electrons being red, then maybe we can agree on photons being yellow. So here are the photons. And now I want to shoot an electron into that. Now, of course, I can calculate the radiation power of that electron. But then I have to calculate the electric and magnetic field components in the rest frame of the electron. So we have to apply Lorentz transforms, and I have to distinguish between the rest frame, that's going to be the primed frame, between the rest frame of the electron and the rest frame of the photons. Okay, so I'm using the Lorentz transform of the field components. Then I know what the acceleration of the electron is going to be like. So the acceleration of the electron in its own rest frame, I can now, of course, calculate with a non-relativistic Larmor formula. Right? Because now I have electrons at rest. But I know that the mean acceleration, well, I need it squared anyway, right? So the mean acceleration squared is now given by E squared divided by ME squared. EX prime square plus EY prime square plus EZ prime square. Okay, and now with the Lorentz transformed field components and applying these formulae for the averages, I can directly work this out. And I get E squared divided by ME squared. Now I get EX squared plus EY squared plus EZ squared. Sorry. I need to take a factor of a third into account if I take just one component of the fields. So I'm getting 4 pi divided by 3c times the energy density in the electric field. Now, I'm getting a factor of gamma square for all of them except for that, but there I have to take this into account. Then from here I'm getting, if I square that, one contribution from the EX squared, a beta square contribution from the BY squared, and 0 contribution from the average of EX times BY. So I'm getting 1 plus beta square from this, I'm getting 1 plus beta square from that, and I'm getting a 1 over gamma squared from the Z component. All right, so that's going to be 4 pi divided by 3c, E square divided by ME square, energy density, gamma square. Now, 2 plus 2 beta square plus 1 minus beta square, right? The 1 over gamma square is 1 minus beta square. So that's going to be easy. That's going to be a factor of 3 plus beta squared, right? So I can write this as 4 pi over c E square over ME square U gamma squared. Now I've taken a factor of 3 out. What remains is 1 plus beta square divided by 3. Okay. Now let me very quickly finish inserting this into the Larmor formula and then stop right now. So the non-relativistic Larmor power, that was 2e square divided by 3c cubed times that, right? So times the squared acceleration. So that's what it looks like. Now you see very beautifully, this gives us a factor of 8 pi over 3 times the classical electron radius squared times the energy density times squared gamma squared 1 plus beta squared over 3. I made a mistake here. This C does not appear. Sorry. And then we get a factor of C here. We have the Thomson cross-section again. And this is the result that I want to close with, and now I have to run away. Sorry, no questions now. Save them for Wednesday. See you then. Das wird schwierig.